from the network perspective to actually make a streaming box awesome. And you know, he's going to be giving some cool stuff on that. But let me just get started. So back in the days, a while ago, this is how telco infrastructure looked like. Now you had different boxes like message routers and intrusion prevention system, and the way it really happens, it's a closed box. So you have a proprietary hardware, a proprietary control layer, and then a specific application that runs on top of it. And you know what? For some time, telcos were actually fine with this. The reason is because they were addressing the demand of the current generation, of their current generation customer, and they didn't care so much about the future. Because they didn't see in any foreseeable future, they didn't see that sudden change in technology is actually required. Now, what really happens is that because all these functions are in a silo, whenever you need more than one router on a particular location, you just go, you have a one-to-one relationship with the vendor, you just go tell him, you get a box, you manually put it, and your admins configure that. And the innovation actually happens at the vendor's hand. So they decide when the product manager, you know, who's sitting in a nice office, he makes a decision. This is when we're going to come up with the next product, so I'm sorry you have to wait. But then came applications of tomorrow. What this really means is that just in 2015, we had 15 billion devices that were actually connected to the internet. That's humongous, and they were generating exabytes of data. What that really means is that these things, they directly go attack, you know, they go hit this telco infrastructure, and these could be smart devices like smartphones, smartwatch, you know, smart whatnot. And now that they've opened up the platform, you can also run some cool applications on top of these devices. And in short, you know, there is a humongous influx of data. And now, all of a sudden, the infrastructure is no longer capable because the speed at which the data rate actually increases is exponentially more than the speed at which you can actually bring innovation to the infrastructure. So all the hell broke loose, and they needed a better answer for this problem. So what they did is that they came up with a new network model. It's called virtual appliance. And the key over here is move away from the proprietary hardware, just stick to the standard x86 platform that is a proven tested solution in data center environment. And move all the applications into a software layer. So as you can see over here, it's all about, one more thing is that x86 processors, they really became fast. You have multi-core processors now, 1632 and even more faster cores, and you can actually virtualize them. You have the infrastructure that you need to make this happen, and this is not a rocket science. So we already have this. So the whole point is now we have decoupled the appliance and the application. So let's do some magic with the application. So I can scale out the same way that I've been able to scale out my data center infrastructure, and I can scale out in a way from the application perspective. So I have things like vRouter or VPC. These are called virtual network, VNF, virtual network functions. So what the key message over here is that it completely became a software-based. You have software-defined networking, which is, you know, all about programming your network. You know, that's again decoupling of your switch, your network, and the control plane. So think about this: a Linux guy sits in front of things like Cumulus Linux, and he can directly go configure. He doesn't have to get any CCNA or any certification. That's exactly what this means. And then you have this network function virtualization, which is really the infrastructure for bringing the software and the telco, the softwares like vRouters and the x86, standard x86 platform together. And as I said, VNF, virtual network, virtualized network function, are each of those instances. Now, the cool thing about this is that I can actually break let's say, vRouter into sub-programs, and I can run them on different virtual machines, or I can run them on containers. So, and from the hardware side, of course, all the standard freebies that you end up getting from the hardware side, things like GPDK and SRIOE, which is all about accelerating the data movement to the virtual machines, to the containers from the physical server, occupying the least CPU footprint. But this actually got us the innovation in software. Before I, move forward, I just wanted to showcase. I'm sure a lot of people over here know about this, but I just wanted to paint the picture of the history of OCP and the motivation that was behind this project. So in 1970s, we had mainframe boxes. These were very nice, shiny, big boxes. They can do some stuff, but not a lot of stuff. And then in 1990s, you said, hey, mainframe is screwed up. Let's get scale-up infrastructure. And in 2000, that became old, and we said, you know what? Scale-up is no longer good. Let's do scale-out. Now, the problem with this, however, is that all these three are proprietary platforms. So around that time, when Facebook was becoming popular in 2009, they were growing exponentially with the new servers, millions of likes, millions of videos being posted, photos being posted. And they actually figured out that in a couple of years down the line, if I were to go down this path, then my innovation will be actually stopped by these guys. So what happened was they announced this project. 2 years, Facebook hired some really smart guys. They went down garage and they started working on it. 2 years later, they said, you know what? We are going to open source not just software, but we'll also open source hardware. And that's exactly what gave way to the Open Compute project. And as I said, it's completely open. Anyone can look at the blueprint recipe and build whatever they want. So which means, now let's go back to telco. Telcos are having the same problem, right? I mean, they are able to innovate to a certain extent through software, just like the way how Facebook was able to. But then they are bogged down by the innovation, the standard x86 platform. So they didn't want to be stopped by that. They wanted a control, not just on the software side, but also on the hardware side. And that's why it makes a lot more sense to be a part of Open Compute project. And you know what? You're a bunch of really smart guys joining this telco group. I'm sure everyone over here knows about this. 6 weeks ago, they made a huge splash. And this is all about bringing efficient data center hardware design to the telco solution. And that is the next step, which is innovation in hardware. So let's look at some of the innovative, cool stuff that OCP actually produced in just the last 4 or 5 years. OCP has been really popular. I mean, not just because of the concept, but it was actually able to deliver something cool. This is a Yosemite platform that Facebook launched last year, and this is the first ever disaggregated host server. Now, what do I mean by disaggregation? Now, typically, if you see in a server, your CPUs are fixed. And then you have add-on cards like network adapter and all the other things that you put them in a PCI slot. So once you want to upgrade, you can only upgrade the adapters. You don't have the option to upgrade just the CPU. And this model didn't really work for Facebook. For all the cool stuff that they were doing, this really didn't work for them. So they said, you know what? Let's shift the equation around. Let's fix the network adapter on the board, and then let's have the capability to actually slide in the CPU sleds. So as you see over here, these are quad CPU cards that are just being slid, and then they all share one single adapter. What this really means is that now I have compressed the power of 4 servers into one box, reduced the number of cabling infrastructure, switches, ports, and also the adapter by almost 4x times. And this is really the innovation. And we are proud to be part of this innovative, cool stuff that Facebook came up with. The other guys, Quanta and Intel, really worked hard, and we are excited to really see this product out. Let's look at another innovation that really came out of this project. It's the Open Ethernet with switch abstraction interface. I'm sure you guys were there in Microsoft keynote. They announced the Sonic platform, which was initially called ACS. And if you see in their cloud environment, they needed an agile way in which they can innovate on top of the switches that they already have. But again, it's not possible because you have one switch and a NAS that runs on top of it. So they said, you know what? Let's do something innovative over here. Let's bring a thin abstraction layer that has API on the top where you can put any network operating system, and then anyone who really wants to be a part of it, they can just provide the SDK for the implementation of the API. And a lot of companies work really hard. I mean, you have Facebook, you have Microsoft, who really spearheaded. You have Intel, Dell, Broadcom, Barefoot, Cavium, and also Mellanox. So what really happens is that now you can take any switch that you want, any switch that can support SAI, and you can take any NAS that you want. You can take Metaswitch, you can take Sonic, you can take OpenSwitch or any other NAS that you want, and you make the choice. You really make the choice. You take the best of the breed of the software. Oops. You make the best of the breed. You grab the best of the breed of the software and the hardware based on your application so that you can innovate at your pace and not at someone else's pace. This is another example. I find it a little funny and hilarious. It's not directly to do, it didn't really come out from OCP, but it amplifies the message of OCP. And in fact, you do have a solution today with OCP on this. So what really happened is that when we tried to scale from 10 gigabit network to 40 gigabit network, the easier way to do that was 4x10 lanes. So you just couple 4 lanes of 10 gig, and then you make that as a 40 gig. Now, turns out, few guys, they didn't like it. I mean, few guys, few guys were actually bogged down by this 40, and they needed more. They wanted their network to run on steroids. So we came up with 100 gig, and instead of using 10, we decided to go with 4 lanes of 25 gig. So obviously, it makes a lot more sense to have a single and the dual 25 gig, just like how you have single lane of 10 and 4 lanes of 10 for 40, right? But when we asked, a few of the guys asked, hey, IEEE, can you do something about this? And they said, sorry, we're not interested. But what really happened is guys like Google, Microsoft, Mellanox, Broadcom, and Arista, you can see that these are actually competitors. They're working together for a solution in which they can innovate faster. What they did is that they actually formed a 25 gig consortium, and they said, you know what, screw it, we will do it ourselves. And all of a sudden, here is one example of how a disruptive technology does not have to come from IEEE, but it can actually come from anyone who has the will to do it and who has the need to do it. So with that, I wanted to pass on to my colleague Srinivas, who will be talking about the reference architecture, which is really inspired by the open platform and the OCP.
Thanks, Ramnath. Everyone can hear me. So I think what we wanted to pitch in terms of content delivery model is something that we learned from the Open Connect platform that Netflix has. So if you look at what they have there today, and let's ignore the details in between, as an end user, as soon as you push the play button, the content's pretty much coming to you from a whole bunch of different cache boxes or pods. It's not coming from a single data center. So the person watching the same video in the US and in China is not getting the content from the same server, obviously. They have layering of caches and power boxes. I just want to take the slide and show the advantage of doing like a similar design between the POP and the cache boxes. The cache boxes are pretty much inside the ISP or at the edge of the network, and they don't have to traverse the entire ISP network to go fetch the video content, which could be pretty high in terms of the network footprint. And there's a reason why the POP boxes and the cache servers are colored similarly. The idea being here that the modular unit of a cache server is something that can be used to connect up as a POP box or a catalog server. So as soon as the content is ready, it's pushed out to the POP servers. The POP servers themselves can talk between each other and not have to rely on the origin to get content from the catalog. And for all the content that's very frequently used, they can be pushed to a closer node, which is the cache server. And the end user basically has a quality of experience that is much more enhanced than having to go back and forth through the network. So to break it down, what it takes to build a cache server is three things, is what we think. Deployability, meaning that it should be scalable, scale out per se, not scale up. So a single box or a set of boxes should be able to be connected together to form both your cache server or your POP center. Security, these boxes, these cache servers go in places that are not necessarily the highest security. People can break in, they should be tamper-proof. Content diversity. Quality of service is like a big deal here. When you start talking about videos, these are videos that are pretty much served as web servers. And so when you use TCP, for example, there are lots of congestion requirements for TCP that can really hamper the quality of experience for the user. So there's a lot of QoS features that I'll talk about in the next few slides that basically enable CDN architecture. Storage media, we started with spinning disks. We have flash drives now. NVMe is coming up. There's a whole variety of storage media form factors that we need to support in this architecture. And in addition, it's also not just the form factor of the storage media, but also the content. There's streaming media, there's live media, both of which have different requirements in terms of latency and throughput and so forth. And then there's also connectivity. Remote access, obviously. Every time a box fails, you cannot expect to send an engineer out to go fix this box. This box has got to be remote accessible. And at the same time, optics plays a big role. Single mode connectivity or connectivity to existing equipment is a big deal. We cannot completely change things. You've got to play with what's already available and then scale up from there. So we got these boxes from Sanmina, and we took Netflix as a reference design, or they took Netflix as a reference design to build these out. I do have one sample up here. We can talk more about it. The lid is open, and we can take a look into this. But what this essentially shows is there are three modular designs available here. There's a 1U form factor, there's a 2U form factor, and 4U. Depending on how much content you want to store, and what combination of spinning disks and flash storage that you want to do, you can choose one of these three different form factors to build out your cache server and the POP design. We'll not go through the details. I think Sanmina Newisys has these version numbers available on the website to go ahead and reference. Again, I think this is just a picture that we got about how POPs are deployed with these cache servers. Essentially, a collection of these boxes put into racks and whole catalogs being stored within these POPs. So in terms of software features, this paper by Randall Stewart at Netflix talks about how using FreeBSD, they got to 40 gig with one of these cache servers. So using classic, essentially what's happening here, it's a web server model, meaning all the content that's stored in a box like this, in all the storage, is sent out through the NIC as a web server. It's a classic Nginx as a web server in the back end, FreeBSD running as software, and contents being pulled out through HTTP requests over TCP. And when this happens, using just out-of-the-box Linux, what they saw was they were getting 4 to 5 gigabits per second. And you can obviously use advanced hardware. We got in some, interesting links for that, and they were still able to just go like twice as much, which is still quite a bit away from 40 gigabits per second. And then there was this interesting piece of software available within FreeBSD, which is sendfile, which is a rewritten sendfile, which basically took advantage of the caching mechanism. So one of the bottlenecks was that every time the kernel requests a content to be delivered to an end user, what was happening was the kernel was taking a copy from the storage, making a local copy in the RAM that the CPU can access. And this copy was then taken to the network socket, copied again in the RAM, and then sent out through the network socket. So it's pretty wasteful to have 2 copies, and then the CPU having to move 2 copies within the kernel on the RAM. If you get rid of it using some of the changes in send file and VM caching that was provided, you're able to push out up to 30 gigabits per second. Now, what was then changed, and I don't know too much about this, the paper actually does a very good job about describing it, is prefetching. And it's one of these old techniques where you decide to pull data expecting that this might be used, and then 99% of the cases this is used, and 1% when it's not used, you pay the penalty. And that actually did improve, and they were able to do up to 40 gigabits per second coming out of the box. So this was, I think, the road to 40 gigabits per second that I think was brilliant in terms of CDN. We're able to take cache boxes now, take a standard web server, put Nginx, put FreeBSD, and be able to run a CDN architecture that scales across the network. But videos are growing. You have more and more videos, education, entertainment, pick an industry, everyone wants to do videos. And there's also a reason to do videos. It makes telepresence all the more better with live streaming videos, live or streaming videos. So what happens when you go to 100 gig? If you want to scale from, say, 40 gig to 100 gig, if you want to fill a box. As Ramnath mentioned, CPUs obviously are going more beefier. But it's impractical to think that all of the TCP requests need to go up through the TCP, need to go up through the CPU, go up the Linux stack, have be serviced by the user application, and then send out. And you would still be able to do 100 gigabits per second. It's literally not possible software-wise, no matter how beefier the CPU gets, which is where the offloads come in. A lot of these TCP stacks, they've been written with legacy in mind. They've been written to be backwards compatible with legacy, which means there's a lot of repeatable code in that we can take advantage of and offload onto a network interface card, which is what some of these offloads are that I'm talking about. So the TCP itself, one of the things that happens is that there's a lot of acknowledgements that go out. So when you say, let's say a video file is, say, 64 kbytes that you want to send in chunks of 64 kbytes. As a TCP, now you start to break down these into tiny, tiny packets that the network has negotiated with the rest of the network. And then every time you send out a packet, the link partner is going to send you an acknowledgement back, and then goes up the trust TCP stack. And now you send the next tiny chunk. I mean, you can imagine how wasteful this can be if you start doing this back and forth, which is where TSO comes in. In TSO, the CPU or the Linux stack can pretty much just say, here's a chunk of data, and I know that you will increment the sequence number and increment the checksum for me. And if there's any fault, you can send me an update on this. I will resend this entire chunk back to you again. And more often than not, there isn't any fault. If the network is good, the packet goes out in these tiny chunks, and this offload pretty much takes away the CPU from having to. The CPU can now context switch and go start doing other uses in the application space. Likewise, on the RX part, we have large receive offload. What LRO does is basically when a packet comes through, again, TCP on the link partner side is sending you tiny chunks of data. You can assimilate all these chunks of data and then have it sent up to the Linux kernel without having to have the TCP stack in your side send out acknowledgements. Now, the other piece of offloading that we do is called RSS, or receive side scaling. What this does is when you have all these cores on the CPU, you want to make sure that all of the cores are equally balanced. You want to make sure that all of these cores are equally loaded. One core is not loaded more than the other, and that all the applications of the users that are being connected are serviced equally by all of the cores available. That's what RSS does. RSS is basically a hashing mechanism where you take the packet coming in and use a hashing mechanism that you can control to distribute where the packet should go to different cores within the CPU. Virtualization is another aspect that actually, I think Ramnath touched upon this in his slide too. There are two kinds of virtualization that we support, which we think would make a lot of difference when it comes to having multiple guests sitting on a host machine talking to end users. SRIOE is a virtualization where the guest operating system can directly talk to the NIC and take advantage of what's available without having to go through a hypervisor or a software abstraction that takes away some of the capabilities available. On the other hand, the hypervisor provides you a level of abstraction which makes your applications portable, which is where you can take advantage of OVS offload, which is Open vSwitch. So if you're running an Open vSwitch and having these different apps running on top of your hypervisor, instead of having all of these applications go through the hypervisor on the CPU, some of the code can actually be offloaded onto your NIC. We also touched a little bit about storage. One of the things about storage is there's a lot of repeatability when you do, say, RAID techniques or when you take backup copies and so forth. There's a lot of checksumming that happens, which doesn't have to be done on the CPU. You can actually take a lot of these checksumming and put it onto the NIC, and this way the CPU can again go back to focusing on the user space. Another interesting aspect is NVMe over fabrics. As we were talking about earlier, as things are going from spinning disk to flash to NVMe, which is basically storage connected on the PCI card, it's a lot of companies today, and you can go back up the booth and find out, have drivers available, which basically let NVMe cards be accessible, be bootable from the CPU. So NVMe over fabrics is an idea where this NVMe card is actually visible across the network to everyone. And the underlying technology for this is a lossless transmission protocol known as RDMA. And there are multiple ways of doing RDMA, both on the software side and on the hardware side, which basically enable doing the storage across the network. So yeah, I kind of went through these slides a little too quickly. Before I talk about future work, I wanted to kind of pitch how telcos would actually fit into the space. And one of the things that we thought about was, just as AWS did with cloud platforms, they were able to take the cloud out of your individual data centers and glom it together in a centralized work. CDN could be a service that telcos could provide. You could have something like a private cloud CDNs could have within their backbone, within their edge networks, so that back and forth requests from the users to the data center to the pods doesn't have to go through the entire network. This would connect, or this would reduce much of the latency, and terminations at the edge of the network would be a lot more beneficial in terms of network utilization. And obviously, there's a lot of work to be done here. For starters, the demo that we have here is based on PCI. We want to take it to the OCP form factor. So a lot of advantages of taking it to the OCP form factor. We have like remote sensing and monitoring that OCP provides, which is really useful for being able to reach out to servers where you cannot actually have live people go and take a look at. The other work, and I'm not touched upon, but it's actually part of it, is the switching, routing, and connectivity part of it. Obviously, when you start putting together a POP server, a bunch of servers connected together, a switching system is required. Something that takes an aggregation for all of these servers to happen. Now that switching is, again, as Ramnath touched upon, there's SAI, there's Open Ethernet. We do have to standardize this on something that can be easily adopted. In terms of cabling, single mode fibers are generally available, and single mode fibers would be the way to go with this, given the connectivity that already exists today. But we need to standardize on the length, the distances, what would be the temperature ranges across which this would work for, and so forth. There's also rack level deployments that we need to talk about, what it takes to get power to some of these racks. If these racks are going to be placed within ISVs, obviously there's got to be a standardization on how DC power is delivered, on how these racks are going to connect with the rest of the data center. Operating systems, we've talked about FreeBSD in this. We know FreeBSD, this is kind of what we looked at in terms of using this concept. But obviously, Linux has the same greatest features that FreeBSD also has. So we want to get as many operating systems on this so that it gives you a flavor depending on how you want to write your applications. Other content formats, we realize CDN is not just about video. CDN is also about text. CDN is also about making sure that your websites can be accessed in the quick time. There are a lot of CDN deployments that already exist today for text and for voice and so forth. And to be able to have this architecture scale back and be able to accommodate all of those formats would be something that needs to be looked into. And more offloads would obviously start coming in. Once you start going into, say, live streaming, then TCP may not be the option. Maybe you need another protocol. And that really, the offloads for that protocol would be something that we need to have to consider. So this is pretty much my last slide. Yeah, we'd love to have more people talk to us and share their ideas and see where this goes. Obviously, the telco mailing list, the tip mailing list would be a place to start. Yeah. We also have an email that you can reach us if you have questions, feedbacks, or comments.
Great.
Thank you.
Thank you. I'm sorry we're, like I said, we're getting compressed for time. We're a few minutes late now, starting with the next session. So if there's questions and comments and stuff, obviously contact
stream us.
Stream or
mailing list is fine.
yeah, or the telco's mailing list as well.
Great. Thanks.
Thank you.